Alright, let's not wait no more. Today's topic will be quite short. It is the topic is one little trick. It's part of our Breakfast with MSA series, and it is a topic number 4 in the line of those. And in the line of those is quite adequate here because we will be talking about trend compensation with a line. So let me share my favorite whiteboard. Here it is. This trend compensation is part of an evaluation of the measuring system of MS. So please keep that in mind, that this is considering just the measurement system. And it is mostly employed when we do repeated measurements of the object. And the object is the produced part. You may remember that in connection with the repeatability error on the measurement system, we always talked about reference rather than an object. And this is the two words that which make the difference within this terminology. The reference is the nice, polished, precise part, and the object is the real one which is being produced and which will be measured in the measurement process. Many times we may have a good motivations to measure the object rather than the reference in the MS experiment, and that's notably when we don't have the references and maybe we don't have enough of them to measure the linearity. For the linearity, as we talked about it last time, we should have at least 5 specimens of different sizes, and this is not really easy to do with the references. So that will be the primary motivation. All right, if we have an object, what sometimes happens, and it's not really exceptional, is that the measurement system is actually changing the measured object. And the example which I have here is that we measure an internal diameter, and this internal diameter has a mark of a production tool, and that's what marked right here. So when the tactile measurement goes in, it has a tendency to flatten these lines, these marks. So in this case, when it is an internal diameter, the diameter increases. And quite often, we can see this trend as it is marked on the graph here with an increasing tendency on the chart. And let me tell you that this phenomenon is not really covered by any of the standards that deal with the measurement system analysis. It's not in the ISO, it's not in the MSA, and it's not in the VDA5 standards, in none of them. So, speaking about that, the question now is, what is the actual equipment variation on a reference? How broad is it? Is it this blue region covering it from min to max, or is it the width of the region in which this trend goes on? In Yarvin, you'll have the opportunity to do both. Pair what you feel is the right thing. And generally speaking, if this tendency, if the increase or decrease of what you see is an effect of an object which is being measured rather than a measuring system, it is completely all right to eliminate that trend, because within the measurement system analysis, we only care about the uncertainty the measurement system is producing. And in this case, we are in fact putting in a part which has a different dimension than it had before. So it is completely all right if the measurement system shows a different dimension in the end. It's not a problem of the measurement system. It actually shows that the measurement system is actually doing something. And that is a very good reason to account for that and not to penalize the measurement system with such a broad estimate of equipment variation uncertainty. All right, so I'll switch now over to Martin, who will show how this is done in Yarvin, and where it helps and where it does not. Martin, please go ahead. You're on mute.
Yeah. Good morning. So, for the demonstration how it works in Yarvin, I have prepared this simple case, simple VA, where we have 5 characteristics. And we have all their properties that are needed for MSA or Validation Act evaluation. So we have some limits, and we have one master with the reference values. So this is the Validation Act we will work with. We have performed the measurements. In this case, it's some kind of 3D measurement system. And we get the results. Sorry, here we get the results. And what's important in this overview is this last column, where is the trend quotient. This number shows us how much will differ the results when we try to compensate the trend. And it is calculated to QMS, to the overall results. So, for example, in this first characteristic, the trend quotient is about 19%. So, when we will compensate this trend, the result, the QMS decreases about 3.5%, which is quite a lot. And we can see what's happening in here when we decreases when we compensate this trend. You can see that the EVR uncertainty decreases a little bit, but also the uncertainty from bias decreases a lot. So this is the reason why we get the better results, because due to trend compensation, we have lower EVR and lower bias. And you can show it, or I can show it how it looks in the graph, because you can see that these lines that shows us the variability of the measurement system are without the trend compensation are parallel to the x-axis. With the trend compensation, it's a little bit skewed. And why this has happened, that will be explained by Jaroslav in a moment. I will just show you the other cases we have, because due to trend compensation, here can be three different cases. We have the first two characteristics that with the trend compensation will be better, because you can see the trend quotient is quite high. Then we have those two, characteristic number 7 and 9. You can see that the trend quotient is basically equal to 1. That means that here are basically no trend at all. Nothing changes when you try to compensate the trend. And the last is characteristic number 10, roundness 1. And you can see that in here, the trend quotient is less than 1. And that means when you try to compensate the trend, you can see that the results are worse than before. And that's happened. And this is due to we have EVR is smaller than without the trend compensation, but bias is higher. And because the increase of bias is bigger than decreasing of EVR, that's the reason why we get the worse result in the QMS. So this is the demonstration how it works in Yarwin. Jaroslav, back to you.
Thank you very much. All right, so what is actually going on there in the background? So first of all, we have chosen to eliminate the trend. So switching from the blue example down to the yellow one. And the uncertainty of the measurement system, that is this UMS thing, it is calculated as a square root of sum of squares of the individual uncertainties, and there is a number of them. These two are not the only one, and they react differently to the elimination of the trend. The equipment variation, the width of this band, it always decreases. It can at most stay the same, but if you try to eliminate the trend, and you will find out that it is not exactly the straight line, that it is inclined in either way, it will always decrease. But there is also the uncertainty from bias, from how off the measurement result is in a systematic way. And in this case, it very much depends on where is the theoretically correct value. That's this XM down here. So if there is a question, what is if we don't longer have the comfort of calculating the average value as the one which is actually the characteristic or the typical one the measurement system is producing. It will not be the average value. It will likely be something what was measured in the first place. So what is being done, that as the characteristic value measured by the measurement system is the one on the line showing the trend, at the point of the first measurement. And in this case, as I've drawn it here, it is almost exactly the black point, the measurement which was produced. So if the correct value, the xm, is somewhere in the vicinity of the first measurement, then the uncertainty from bias will also decrease. But if it is somewhere in the vicinity of the last measurement, the bias to the first measurement increases. And if the change in the bias, in the increased bias, is a greater than a change in the uncertainty from equipment variation, then you will make the whole thing only worse. By eliminating the trend, you will increase the uncertainty, so the overall characteristic, the QMS Martin has shown, will increase. So not always elimination of the trend will help you. So the chapter we have in every one of these webinars, what to do when it goes wrong. First of all, if you see a trend, and this trend is showing incapable measurement device, then you have a chance to eliminate it. But please do this only if you think, or if you are sufficiently confident that this is coming from the change of the measured object and not the change in the measuring system. Because if you will be grinding off the measurement system, then there is no justification to actually do the elimination of the trend. So that's one point. And then the other, if you eliminate the trend and it makes things worse, then you need to do something about the systematic error of the measuring device. It means that that just by coincidence, the measured value was actually achieved, but only after something was shaved off either the measured object or the measurement system. And this is not good. In this case, you need to shift either something in the measurement system, or it can be in the reference, or it can be in the scale, somewhere in the region. You need to shift the systematic value the measuring device is producing to fit better with the initial value the measured object had before it started to be changed by the measurement system. Alright, this is all from us for today. Do we have any questions?
We are here to make it run. We are here to have some fun.
No, there's
We
no
are
question.
here to
Chat
work real hard.
Q&A.
We are
Then
here to
thank you very much, and
make
we are
you
looking
smile.
forward to see you the next time.
Deary bat, we are deary bat. Deary bat, we are deary bat. Deary bat, we are deary bat. We are deary bat.